Hey everyone, welcome to episode 2 of Miss Blue's Calculus Clues. I am back again to talk to you today about particular solutions to differential equations. So yesterday's video talked about general solutions to differential equations, which was just really a fancy pants way to talk about finding the antiderivative and an expression for all the possible antiderivatives that would yield a particular differential equation. So today we're going to take that conversation kind of to the next level and talk about particular solutions to differential equations. And the difference between these two types of problems is when we're asked to find a particular solution to a differential equation, we are given what we call an initial condition. An initial condition is a piece of information that tells us, and it's a piece of information that we can use to determine which exact antiderivative is the one that we are looking for. So let's look at a couple of basic examples first, and then we'll do one together that also requires a separation of variables. So particular solutions to differential equations. So let's consider a pretty simple example first. Let's consider the differential equation dy dx equals 1 over x squared. And the initial condition, or the additional piece of information that they are giving us in this case, is that y of 1 equals 4. And that's telling us that the particular antiderivative that we are looking for must pass through the coordinates 1, 4. And we'll be able to use that piece of information to assist us. So I look at this differential equation, and the first thing that I want to do is I want to find the general solution. And I'm looking at this differential equation, and then I notice that it is exclusively given to us in terms of x, and it's the kind of differential equation that I can simply think about and work backwards to find the antiderivative. So if I were to work backwards here, to find the antiderivative of 1 over x squared, I would use the derivative power rule, but working backwards. So I can think of dy dx in this case as x raised to the negative 2 power, which means the antiderivative of that would be y equals negative x to the negative 1. Now, I'm going to initially start with my general solution to this differential equation, which would require that I have a c here, that constant. So this is my general solution. I am now going to use the initial condition that I was given to find the particular solution that I'm looking for. And the particular solution, again, is just a fancy way of saying I want one exact or particular antiderivative. And the antiderivative that we're looking for must contain the 0.14. So what I'm going to do is I'm going to plug 4 in for y, and I am going to plug 1 in for x. Now, when I do that, I can then solve for my particular constant c. So 4 equals negative 1 over 1 plus c, so c must equal 5. So now I have taken that initial condition and what I know about antiderivatives to find a general solution, and I'm putting those two pieces of the puzzle together to find a very specific antiderivative. The antiderivative that we were looking for is y equals negative 1 over x plus our constant 5. This is the particular solution that we were looking for. It is a function whose derivative is 1 over x squared, and it also passes through the point 1, 4. So let's take a minute and look at a second example here to give us an idea of how these can look in action with a little trig, because I know how much you all love trig. So let's take a second and look at a slightly different differential equation with different initial conditions. So this is our second example. Let's say we want to find the particular solution to the differential equation dy dx equals -2 times sine of x, with the initial condition that y of pi over 2 equals pi. Now, that's a really fancy way of saying that we are looking for the antiderivative of -2 sine x that passes through the point pi over 2 pi. So the first thing that I'm going to do is I'm going to look for my general solution to my differential equation. Again, just as in this last example, the derivative given here is exclusively in terms of x. So I can think backwards about my functions and to find my antiderivative. So when I integrate each side here, I will determine that y is 2 cosine of x plus c. Notice again, I'm finding my general solution first, so I have added my constant c in here. Now that I have done that, I am going to plug my initial conditions in so that I can determine what the value of c would be. So I am going to take y and I'm going to replace it with pi. And then I am going to take x and I'm going to replace it with pi over 2. So the cosine of pi over 2, everyone come on, make Mr. Ryan proud. Bust out that unit circle. And determine that the cosine of pi over 2 is 0, and 2 times 0 is 0. So then c must be pi. So this was my general solution. And I have now taken that general solution and the initial condition that was given to me and determined that the particular solution is y equals 2 times the cosine of x plus pi. So far, so good? All right. So let's look at one last example that requires a separation of variables. My daughters have been working on a theme song for this YouTube channel. So over the next couple of days, hopefully we will get a good, clear audio recording of that for you all to enjoy. All right, so last particular solution to a differential equation of the day today. We've got dy dx equals 2x over e to the 2y. And our initial condition here is that y of 2 equals 1/2. So the first thing, again, just as with the other examples, we're going to start by finding our general solution first. Now, this third example differs from the other two with respect to the fact that it has the differential equation has both an x and a y in it. Therefore, I'm going to need to use the separation of variables to find my general solution. So the first thing I'm going to do is I'm going to isolate all my y terms on one side of my equation and all my x terms on the other side of the equation. So I have e times 2y, e to the 2y dy equals 2x dx. And now I'm ready to integrate both sides here. The antiderivative of e to the 2y dy would be 1/2 e to the 2y. And the antiderivative of 2x would be x squared. Now, again, just as in last time, I do not wish to really complicate things by having constants on both sides. So I'm just going to put a constant on the right-hand side of my equation. Now, I really don't like the way this looks with my y being up in the exponent here. So I'm going to do a little bit of algebraic manipulation to make my life a bit easier. So the first thing I'm going to do is going to multiply each side of this equation by 2. So to cancel out this 1/2. So I have e to the 2y equals 2x squared plus c. Now again, I could write 2c, but 2c is just another constant. So to keep my life as simple as possible, I'm just going to keep that constant as c. Then I am going to take the natural logarithm of each side. By doing that, the natural logarithm and the base e are inverses of one another. In doing that, I can then solve for y. So I know 2y equals the natural logarithm of 2x squared plus c. Then I am going to divide each side by 2. So y equals the natural logarithm of 2x squared plus c divided by 2. Now this, my friends, is the general solution. I have so many arrows going on here. That is the general solution, but we want to find the particular solution. So to find the particular solution, that's just a fancy way of saying I need to be able to solve for c here. So this is telling me that when I plug in 2 for x, I will get 1/2 for y. So y is going to be 1/2 when x is 2. Now, as I look at this, what this is telling me is that my numerator here must be 1. So we're really looking for when the natural logarithm of 8 plus c equals 1. Give me 1 second. Thank you, Corinne, for your assistance there. She's like Vanna White. So we have 1 equals the natural logarithm of 8 plus c. Now, if we were to think about that with respect to base e here, e raised to the first power equals 8 plus c. And therefore, our constant c must be e minus 8. And so now I can write out my particular solution to this differential equation, taking c and replacing it with e minus 8. And there's our particular solution to our differential equation. I hope you guys found this helpful. Please feel free to take notes on these. Watch it as many times as you need. I'm going to be having you work on some practice exercises in Khan Academy that will be giving you a lot of immediate feedback. So I hope you find this helpful. Keep asking questions, keep communicating, and I look forward to talking to you all soon.